This is section 9.2, Components of Vectors. Let's start it with a few definitions. The first one is the position vector. A position vector is a vector whose initial point is at the origin of the rectangular coordinate system. In this image, we can say that vector A is a position vector because its initial point is at the origin of the rectangular coordinate system. In this image, we see two more vectors, and these are a sub x and a sub y. A sub x is called the horizontal component of vector A, and it is located on the x-axis. Vector a sub y is called the vertical component of vector A, and it is located on the y-axis. Now, if we look at these two vectors a sub x and a sub y, we see that both of them start at the origin, and if we form a parallelogram, then we can say that vector A is the sum of vectors a sub x and a sub y. So, by the parallelogram method, vector A represents the sum of the vectors a sub x and a sub y. But if we are given vector A and we have to find the components a sub x and a sub y, this process is called resolving the vector into its components. Next, we will see how to find the horizontal and the vertical components of vector A. In this image, we have a vector A, and this vector has a certain magnitude, and the angle that forms with the x-axis is angle theta. Let's see how we can find the horizontal and the vertical components of vector A. From the terminal point of vector A, we will draw a perpendicular down to the x-axis. Then a right triangle will be formed with the bottom side a sub x, the right side a sub y, and the hypotenuse a. In this triangle, cosine of angle theta equals the adjacent side a sub x divided by the hypotenuse. So, cosine of angle theta equals a sub x divided by a. If we multiply both sides of this equation by a, then on the right side a and a will cancel, and we will have that a sub x equals a cosine of theta. And this is how we find the horizontal component of vector A. Also, from this triangle, sine of angle theta is the opposite side a sub y divided by hypotenuse. That is, sine of theta equals a sub y divided by a. If we multiply both sides of this equation by a, then on the right side a and a will cancel, and we will get that a sub y equals a sine of theta, and this is how we find the vertical component of vector A. Now, let's solve exercise 5 on page 270. In this exercise, we are given a vector with the magnitude of 750 and an angle in standard position of 28 degrees. Then we will find the horizontal and the vertical components of this vector. For the horizontal component, we will use the formula a sub x equals a cosine of angle theta. For this vector, a sub x equals 750 multiplied by cosine of 28 degrees. Then a sub x equals approximately 662 units. Now, to find the vertical component, we will use the formula a sub y equals a sine of theta. Then a sub y equals 750 multiplied by sine of 28 degrees. A sub y will be equal to approximately 352. So, on the graph, if from the terminal point of vector A, we draw a perpendicular down to the x-axis and another perpendicular to the y-axis, then the vector that is along the x-axis is the horizontal component of vector A, and we call it A sub x, and the magnitude is approximately 662, and the vector that is on the y-axis is the vertical component of vector A. We call it A sub y, and the magnitude is 352. Now let's see a similar problem, and this will be exercise 8 on page 271. Here we are given vector A with the magnitude of 750 units and the angle in standard position of 307.6 degrees. We will find the horizontal and the vertical components of this vector. For this, we will use the same formulas we used in the previous problem. For the horizontal component, A sub x equals A cosine of theta. And for the vertical component, A sub y equals A sine of theta. First we will find A sub x, so A sub x equals 750 multiplied by cosine of 307.6 degrees. Then A sub x equals approximately 458 units. And now the vertical component A sub y equals 750 multiplied by sine of 307.6 degrees. Then A sub y equals approximately negative 594. Now let's draw these components on the graph. From the terminal point of vector A, we will draw a perpendicular up to the x-axis and another perpendicular to the y-axis. Then the vector on the x-axis will be the horizontal component of vector A. We will call it A sub x, and A sub x equals 458. The vector on the y-axis is A sub y, and A sub y equals approximately negative 594. Notice that this vertical component is represented by a negative number, and that is because this vertical component is located on the negative y-axis. So the rule is that if a horizontal component is directed to the right, then it's represented by a positive number, but if it would be directed to the left, it would be represented by a negative number. The same is with the y component. If the y component would be directed up, then it would be represented by a positive number, but if it's directed down, it is represented by a negative number. Now let's solve some word problems that involve vectors. On exercise 21, on page 271, we have the following word problem. A nuclear submarine approaches the surface of an ocean at 25 kilometers per hour at an angle of 17.3 degrees with the surface. What are the components of its velocity? So here we have the surface of the ocean, and this is the vector that represents the velocity of the submarine. The magnitude of this vector is 25 kilometers per hour, and the angle that it forms with the surface of the ocean is 17.3 degrees. We will find the horizontal and the vertical components of this vector. This is the initial point of this vector, and we will place it at the origin of the rectangular coordinate system. Now, if this angle has the measure of 17.3 degrees, then this angle will also have the measure of 17.3 degrees. And this is because these two angles are called alternate interior angles. Now let's find the horizontal and the vertical components of this vector. For the horizontal component, A sub x equals A cosine of theta. And for the vertical component, A sub y equals A sine of theta. Then A sub x equals 25 cosine of 17.3 degrees. Then A sub x is approximately 23.7 kilometers per hour. Now a sub y equals 25 times sine of 17.3 degrees, and a sub y equals approximately 7.43 kilometers per hour. Now on the graph, if from the terminal point of the given vector we draw a perpendicular down to the x-axis, then the vector along the x-axis will be the horizontal component, ax, and will have the magnitude of 23.7, and the vector along the y-axis will be the vertical component, a sub y, and will have the magnitude of 7.43. So we can say that the horizontal velocity of this submarine is 23.7 kilometers per hour, and the vertical velocity of this submarine is 7.43 kilometers per hour. Next, we will solve problem 24 on page 271. A car traveling at 25 miles per hour hits a stone wall at an angle of 65 degrees with the wall. What is the component of the car's velocity that is perpendicular to the wall? We will start by drawing the vector that represents the velocity of the car. We will have this vector in standard position, which means that the initial point is at the origin of the rectangular coordinate system. So here we have the rectangular coordinate system and the vector that represents the velocity of the car. We know that the car hits a wall at an angle of 65 degrees. So to the right we will draw a wall, and the angle formed here will be 65 degrees. The problem is asking to find the component of the car's velocity that is perpendicular to the wall. To find the component that is perpendicular to the wall means to find the horizontal component of this vector. So if this vector is vector A, then the horizontal component we will call it A sub x. Also, in this right triangle, if this angle is 65 degrees, then this angle will have the measure of 25 degrees. As we see, the sum of these two angles makes 90 degrees. Now let's find this horizontal component, a sub x. A sub x equals a cosine of theta, then a sub x equals 25 times cosine of 25 degrees. Then a sub x equals approximately 23 miles per hour. And this represents the car's velocity that is perpendicular to the wall. Now we will solve exercise 30 on page 271. A water skier is pulled up the ramp shown in figure 9.19 at 28 feet per second. How fast is the skier rising when leaving the ramp? Here's the ramp shown in figure 9.19 with the bottom side of 9.5 feet and the right side of 2.5 feet. So again, in this triangle, we are given the dimensions of the ramp. But now to the right, let's draw a similar triangle to this one. Both these triangles have the same acute angle theta. However, in the triangle to the right, we will have a vector that will represent the velocity of the skier. And the velocity is 28 feet per second. To find how fast the skier is rising when leaving the ramp means to find the vertical component of this vector. We will call this vertical component a sub y. But to find this vertical component, first we have to find the angle theta. And we will find this angle theta by using the dimensions of the first triangle. We know that the tangent of angle theta equals the opposite side divided by the adjacent side. So then tangent of angle theta equals 2.5 divided by 9.5. To find angle theta, we will take the tangent inverse of 2.5 over 9.5. Then angle theta is approximately 14.74 degrees. And because these two angles are the same, this angle is also 14.74 degrees. Now we can find the vertical component by using the formula a sub y equals a sine of theta. Then a sub y equals 28 sine of 14.74 degrees. Then a sub y equals 7.1 feet per second. So now we can say that the skier is rising at 7.1 feet per second. Now here we have a problem from the handouts. A fire is moving toward a highway with the speed of 12 feet per second and an angle of 50 degrees with the highway. What is the component of the velocity toward the highway? First, let's draw the highway. Now we will draw the vector that represents the velocity of the fire. The velocity of this vector is 12, and it forms an angle of 50 degrees with the highway. We will place the initial point of this vector at the origin of the rectangular coordinate system. Then, if this angle is 50 degrees, then this one will also be 50 degrees because they are alternate interior angles. And now to find the component of the velocity toward the highway means to find the vertical component of this vector. We will call this vertical component a sub y. Then a sub y equals a sine of theta, or a sub y equals 12 sine of 50 degrees. Then a sub y equals 9.2 feet per second. So we can say that the velocity of the fire toward the highway is 9.2 feet per second. Here we will be done with section 9.2, and this was components of vectors. Thank you.